Myself, Jose Anthony Vijay, Department of Basic Science and Humanities, Rajagiri School of Engineering and Technology, Kakinada. Now, in this session, we are going to study about the light propagation through different types of optical fiber and the refractive index profile of the different types of optical fiber. Now, the first one is the step index single mode optical fiber. Step index single mode optical fiber. The core and cladding, these are the two basic layers of an optical fiber, basic unavoidable layers of an optical fiber. If you take any optical fiber, it will be having core and cladding. A core with high refractive index and cladding with less refractive index. So I'm going to draw the refractive index profile of a step index optical fiber. As I explained in the previous session, step index refers to the variation, how the refractive index profile varies when you move from the center of the core towards the core cladding region. I'm going to draw the structure of an optical fiber. So this is an optical fiber. The core and cladding, these are the two essential layers of an optical fiber because the guiding principle is based on total internal reflection. So this is the core of an optical fiber, core. Refractive index of the core is represented by N1. And this is a cladding of an optical fiber, cladding region of an optical fiber. We usually represent it by the letter N2. And when you compare the core index with the cladding index, N1 will be greater than N2. Core, higher refractive index region, and cladding, the less refractive index region. So this is the optical fiber axis. This is the optical fiber axis. And this is the radial distance, Now I'm going to draw the variation in refractive index. What happens or how the refractive index varies if you move from the center of the core towards the core cladding interface and then from the core cladding interface to the edge of the cladding. So I'm going to draw the variation in refractive index of the step index single mode optical fiber. So I have an axis where radial distance is taken along the x-axis and the refractive index is taken along the y-axis. So the y-axis is the refractive index and x-axis is the radial distance. X-axis is radial distance. So this is my origin. Now, throughout the core, one of the features of the step index single mode optical fiber, that is a core, is having uniform refractive index throughout. As an example, I'm going to take the value of refractive index of the core as 1.5. Let it be. For example, as an example, let the core index be 1.5 and the cladding index N2, let it be 1.4. So if I move to the core region radially, that is from the axis of the optical fiber, if I move towards the left or right, the refractive index remains 1.5 because core is having a uniform refractive index throughout. So this is the edge boundary, that is the core cladding boundary. This is the core cladding boundary. So if I move radially from the center of the core towards left and right radially, the refractive index remains the same, 1.5. So on the y-axis, where I have plotted the refractive index, I am going to take this point. Let this point corresponds to 1.5. So throughout the core region, the refractive index is 1.5. So if I move towards left or right from the center of the core towards core cladding interface, the refractive index is the same, 1.5. So I get a straight line like this. So from the center of the core towards core cladding region, that is towards my left and towards my right. That is the, I'm going to move from the center of the cores towards core cladding interface, right? And from the center of the core towards core cladding interface towards the, right, the previous was left. So the refractive index remains the same since it is having a uniform refractive index throughout, 1.5. Now, what happens on reaching the core cladding interface? The refractive index drops from 1.5 to 1.4, and it remains same. Up to the cladding interface, it remains the same. So on reaching the core cladding boundary, the refractive index drops from 1.5 to 1.4. And cladding region, it is having a uniform refractive index. The value is 1.4. So let this point be corresponding to 1.4. So throughout the cladding region, the refractive index is 1.4. So from 1.5, it drops to 1.2 on reaching the cladding region. This is the core cladding boundary. This is the cladding region. So throughout the cladding, the refractive index is 1.4. Similarly, if you move towards the right, this is the core cladding boundary. On reaching the core cladding boundary, the refractive index is dropping from 1.5 to 1.4. And throughout the cladding region, the refractive index is 1.4. So there is a drop in refractive index when you reach the core cladding interface, and throughout the cladding region, the refractive index is the same. So this is the cladding boundary. This is the cladding boundary. So we can see the profile of the refractive index profile of the step index single mode optical fiber look like a step, and hence the name step index fiber. So that is why it is called step index fiber, step index fiber, step index fiber. That is the refractive index, the way in which the refractive index profile varies when you move from the center of the core towards the core cladding interface, and then from the core cladding interface to the cladding boundary. The variation in refractive index is looking like a step. That is why it is called step index optical fiber, step index optical fiber. That is the profile look like a step. And then we are going to study about the path propagation. Then we are coming out to the next point, that is a single mode optical fiber. Again, we are going to see how light propagates through a single mode optical fiber. Again, the same structure, optical fiber. The core should be having a very small core diameter. So this is a core region. Core region, we represented by the letter. Refractive index of the core is represented by N1. N1. N1 is the core index, and N2 is the cladding index. So this is the axis of the optical fiber. We call it optical fiber axis. Optical fiber axis. In the case of single mode optical fiber, there is only one light ray path, and we call that path as the axial path. There is only one light ray path inside the fiber, that is called the axial path. We call it the axial path. Or we call axial mode, axial path, etc. So this fiber supports only one mode, and hence the name single mode optical fiber. So just summarizing, the case of a single mode optical fiber or step index single mode optical fiber, the refractive index profile look like a step, and the fiber supports only one mode. And one of the advantages of the single mode optical fiber, advantages of the single mode optical fiber is it is used for long distance communication. For example, intercontinental superhighway communication channel. We use this single mode optical fiber. It is not having any losses and all. So we prefer step index single mode optical fiber if the channel communication is lengthier for intercontinental connection, for the internet and all, backbone of the internet, the fiber that is used is single mode optical fiber. Why it is preferred? Because it is having low losses. low loss. The fiber is having minimum losses, and we can transmit data with high speed in the case of a single mode optical fiber. And disadvantages. Disadvantages of the single mode optical fiber. We know this single mode optical fiber is characterized by very small core diameter. The core diameter, I think I have not mentioned the core diameter. This is 8 to 10 micrometers is the core diameter range of a typical single mode optical fiber. So when you use this fiber for optical fiber communication, we need to convert information into light, and this light is being launched into the optical fiber. So that is called coupling. So coupling light into the optical fiber becomes very, very difficult because of the very small core diameter. We have to use coherent light source such as laser. And joining two optical fibers is very difficult. So the splicing, we call it splicing and coupling. Splicing and coupling. Splicing means joining two optical fibers together, and coupling means joining light with an optical fiber. So splicing and coupling is very difficult. That is joining two optical fibers together, and coupling a light source with an optical fiber is very difficult in the case of a single mode optical fiber. So these are the disadvantages of a single mode optical fiber. Next, we are going to discuss about the light propagation and refractive index profile of a multi-mode step index optical fiber. Step index multi-mode optical fiber. So first we are going to discuss about the refractive index profile of a step index optical fiber. This is I'm going to draw the structure of a multi-mode optical fiber. So this is the core of the multi-mode optical fiber, be represented by the letter N1. This is the cladding of the multi-mode optical fiber, represented by the letter N2, with N1 greater than N2. Core higher refractive index region and cladding less refractive index region. Now compared to the step index single mode optical fiber, step index multi-mode fiber has a very large core diameter. You can see that the core diameter is very big in the case of a multi-mode optical fiber, step index multi-mode optical fiber. I'm going to draw the variation in refractive index profile, how the refractive index profile varies. So we are going to draw the refractive index profile, how the refractive index profile, if I move from the center of the core towards the core cladding interface, and then from the core cladding interface to the cladding boundary. So the y-axis is refractive index and the x-axis is radial distance. So my x-axis is radial distance and y-axis is refractive index. Now let the refractive index of the core be 1.5 and refractive index of the cladding be 1.4. So throughout the core region, the refractive index is 1.5. So if you move from the center of the core towards the core cladding interface, towards my left and towards my right, the refractive index is the same. So you get let this point correspond to 1.5. Y-axis is refractive index, let this point correspond to 1.4. So throughout the core region, the refractive index is the same, 1.5. So I get a straight line. This is the core cladding boundary. This is a core cladding boundary. So throughout this core region, that is from the center of the core towards the core cladding region, the refractive index is the same, uniform at 1.4. So throughout this region, the refractive index is the same, 1.5. So I get a straight line like this. On reaching the core cladding interface, there is a slight drop in refractive index, that is from 1.5, it drops to 1.4. 1.4. So you can see that the refractive index profile suddenly dropped from 1.5 to 1.4. That this point corresponds to 1.4, and it continues till the cladding interface. Similarly, towards my left, the refractive index is 1.4. So we can see, so this is the refractive index of the core N1, and this is the refractive index of the cladding N2. So core and cladding, refractive index variation, it's looked like a step, and hence the name step index fiber. So both step index single mode optical fiber and step index multi-mode optical fiber, the common feature of the both is the profile, how the refractive index varies. It looked like a step. But one difference is the step width. In the case of a single mode optical fiber and multi-mode optical fiber, difference is there. Single mode optical fiber is having a very small step width, and multi-mode optical fiber is having a very large step width. So this is the difference. So another difference is the diameter. Core diameter is very large in the case of a multi-mode optical fiber, and core diameter is small in the case of a single mode optical fiber. Now we can see how light propagates through a step index multi-mode optical fiber. So I'm going to draw the optical fiber. So this is the optical fiber. We know it has a core and a cladding. So this is the optical fiber axis. This is my core with index value N1, and this is my cladding. Denoting the refractive index by N2. Now, as the name multi-mode suggests that this fiber will support many modes. Now, light can travel through the axis of the fiber. Now, if it is traveling through the axis of the fiber, it is termed as the axial mode. Axial mode. Now, another mode supported by the fiber is the lower order mode. So this is the lower order mode, which is making a small angle with the fiber axis. So this is the fiber axis, and the angle made by the lower order mode will be small with the fiber axis. This is called a lower order mode, and after making few reflection inside the fiber, it will emerge out to the other end of the fiber. So this is the light propagation of a lower order mode, which makes few reflection inside the fiber. Now, another mode that is supported by the multi-mode optical fiber is the higher order mode, which on entering into the fiber makes many reflection inside the fiber. After making many reflection inside the fiber, it will be emerging out of the fiber. So I'm summarizing this mode supported by the multi-mode optical fiber is axial mode, lower order mode, and higher order mode. Lower order mode and higher order mode. Lower order mode and higher order mode. So axial mode, lower order mode, and higher order mode. So these are the modes that is supported by the multi-mode optical fiber. So variation in refractive index look like a step, and that is why it's the name step index fiber. And multi-mode refers to the path supported by the fiber. It can support multiple modes. The light can travel to the axis. There is a lower order mode and there is a higher order mode. Now, one of the advantages of this multi-mode optical fiber, a few advantages of this multi-mode optical fiber is coupling and splicing is easy. I have explained earlier that is splicing means joining two optical fibers together. For example, if you want to build up an optical fiber communication channel, if it is of 400 kilometers lengthy, we need to join optical fibers together to meet the required length. So in such cases, we need to splice two optical fibers together. So splicing, step index multimode optical fiber is easy. Splicing. Splicing and coupling. Coupling means joining optical fiber with a light source. The splicing and coupling is easy. And because of the large core diameter, we can use LED as a light source. We know optical fibers can transmit light only in the form of signals which are only in the form of light. So we need to convert all information into light format. So you can use LED as my light source. So these are the advantages. Splicing and coupling is easy. LED can be used as a light source. And one of the disadvantages of optical fiber, step index multimode optical fiber is disadvantage. Disadvantage of the multimode optical fiber is it is having loss, dispersion loss. Dispersion loss. Now it is arising due to the different modes supported by the fiber. Now all these light enter into the optical fiber, but due to the different axial speeds, we can see that the lower order mode, axial mode comes first, then the lower order mode, and then the higher order mode. Because axial mode makes no reflection inside the fiber, therefore it will be reaching the other end of the fiber first, and then comes the lower order mode which make few reflection, and then comes the higher order mode which make many reflection inside the fiber. So due to which there is a mismatch in input and output, which we call it as a dispersion losses, which is called intermodal dispersion, and which is arising due to the different speed of the light ray path inside the fiber. So this is all about the step index multimode optical fiber, and we are going to discuss about the last type of fiber, that is a graded index multimode or multimode graded index optical fiber. Multimode graded index optical fiber. Multimode graded index fiber. This is the structure of a graded index fiber. This is the axis of the fiber. This is my cladding region, represented by the letter N2, refractive index. And core, if you take the core refractive index is a function of R. Core refractive index is a function of R. The core refractive index is a function of R. That is, the refractive index of the core varies. That is why it is called gradation. It's not the same. The index value, for example, if you take the refractive index value at the center of the core, let it be 1.5. As an example, 1.5. And the cladding region, it is having a refractive index of 1.4. At the center of the core, the refractive index value is 1.5. Now, if I'm going to take another point over here, that is, the refractive index value will be 1.49. Likewise, over here, the refractive index is 1.49. 1.49. Over here, the refractive index variation is, this is the refractive index value. It is 1.48. This is the refractive index value of this point is again 1.48. Likewise, it keeps on decreasing, and on reaching the cladding, the refractive index becomes 1.4. 1.4. So we can see that in the case of a multimode graded index optical fiber, the refractive index is maximum at the center. The refractive index is maximum at the center. If you move up from the center of the core towards the core cladding region, the refractive index is decreasing gradually. There is a gradation in refractive index. That is why it is called graded index fiber. Refractive index is maximum at the center and it decreases. If you move up from the center of the core towards the core cladding region, if you move down from the center of the core towards core cladding region, the refractive index is decreasing. So there is a gradual decrease in refractive index, and hence the name graded index optical fiber. So index value is maximum at the center and index value decreases as we move from the center of the core towards core cladding region. We're going to draw the profile of the graded index optical fiber. So this is my optical fiber. This is my core, whose refractive index depends on radial distance. It's a function of r, and this is a cladding which is having a uniform refractive index throughout. So this is my axis of the fiber. So I'm going to draw the variation in refractive index. So this is my y-axis and this is my x-axis. The y-axis is the variation in refractive index and x-axis is the radial distance. So at the center, we know the refractive index is maximum. It corresponds to 1.5. So I'm going to take a point on my y-axis that this point corresponds to 1.5 at the center. So this is my origin. At the center, the refractive index is 1.5. So if I move from the center towards core cladding interface, you can see that the refractive index is decreasing because over here 1.5 is the refractive index, 1.49, 1.49, 1.48, 1.48 and so on. And when it reaches the cladding, core cladding interface, this is a core cladding interface, the refractive index becomes 1.4. On reaching the core cladding interface, the refractive index becomes 1.4. So there is a gradual decrease in refractive index. So if you move from the center of the core towards core cladding region, either to the left or right, we can see that the refractive index decreases. And that decreasing process continues till core cladding interface. So this is how it varies. So there is a gradual decrease in refractive index when you move radially from the center of the core towards the core cladding interface. So there is a gradual decrease. At the center, the refractive index is maximum. If you move from the center of the core towards core cladding interface, the refractive index is decreasing. So this is the profile. Now, when core cladding boundary is reached, the refractive index becomes 1.4. Now, throughout the cladding region, the refractive index is 1.4. So this is I'm going to draw the cladding boundary. This is my cladding boundary. So, on reaching the cladding boundary, we can see that the refractive index dropped to 1.4. So I'm going to take this point as my 1.4. So the refractive index will be 1.4. So on either side, the refractive index throughout this region, the cladding refractive index is 1.4. Throughout this region, the cladding value is refractive index value is 1.4. So this is called a parabolic profile. So the refractive index profile, as I explained earlier, how the refractive index vary when you move radially from the center of the core towards core cladding region, the refractive index profile look like A. It is a parabolic profile. Parabolic profile. Parabolic profile. So refractive index profile is parabolic. Now we are going to see about how light propagates through a multi-mode graded index optical fiber. One of the disadvantages of multi-mode step index fiber is intermodal dispersion, which has been minimized in this or totally avoided in this multi-mode graded index optical fiber. Now, before going into the detail of the light propagation of the multi-mode graded index fiber, you should know the basic light rule. That is, light when it travels from denser to rarer. This is a normal, and this is what happens when light travels from rarer to denser. What is happening from light to the light when it is traveled from a rarer medium to a denser medium? We know light when it is traveling from a denser medium to a rarer medium, the light ray will bend away from the normal, the refraction. You know refraction happens, and if it is traveling from a denser to rarer media, the bending will be away from the normal. And if light is traveling from a rarer medium to a denser medium, it will be bending towards the normal. So this is the propagation of light in two different media. denser to rarer, and rarer to denser. This is the normal, sorry. Now, in the case of a multimode graded index optical fiber, the entering light, for example, this is a light that enters into the optical fiber, it is continuously traveling from a denser to rarer medium. We know that when light travels from denser to rarer media, it bends away from the normal. So this is my normal, it bends away from the normal. So refraction happens again. Again, it is traveling from a denser to rarer medium. Refractive index is 1.49, refractive index is 1.48. So again, it is traveling from a denser to rarer medium. So again, the light will bend away from the normal. On reaching or before reaching the core cladding interface, what happens is the condition for TIR happens. We know one of the guiding mechanism of optical fiber is TIR, total internal reflection. And that total internal reflection can happen on reaching the cladding or before reaching the cladding. Now over here, it is happening before reaching the cladding interface. So total internal reflection happens. So due to total internal reflection, the light is reflected back into the medium itself. So now the reflected light is now traveling from a rarer to a denser medium. So what happens to the light? It bends towards the normal. So the propagation mechanism in the case of a multimode graded index fiber is continuous refraction followed by TIR. Continuous refraction followed by TIR towards the interface, towards the core. So continuous refraction followed by TIR towards the center of the core. So this is the guiding principle in the case of a multimode graded index fiber. So continuous refraction followed by TIR, and this TIR can happen on reaching the core cladding interface or before reaching the core cladding interface. So this will be the path of light inside the fiber. It supports many modes. This will be the path of light inside the fiber. This is the light ray path inside the fiber. This is the axial mode, which is having no refraction at all. This is the lower order mode, and this is the higher order mode. So this is the light ray path inside the multi-mode graded index fiber. So I'll repeat once again. The guiding principle in the case of a multi-mode graded index fiber is continuous refraction, which is arising due to this special graded index profile. So continuous refraction followed by TIR towards the core. And this TIR can happen on reaching the core cladding interface or before reaching the core cladding interface. On reaching the core cladding interface or before reaching the core cladding interface. So this is a guiding mechanism in the case of a multi-mode graded index optical fiber. I'm going to discuss about the advantages and disadvantages of this multi-mode graded index fiber. These are the advantages. Now, because of this parabolic profile, there is no intermodal dispersion. We know this type of dispersion arises due to the different speeds of the light in the fiber. Now, because of this parabolic profile, all light ray path takes same time to travel a particular length inside a fiber. So there is no intermodal dispersion. And fabrication, there is a disadvantage. That is, it's difficult to make this multi-mode graded index fiber.